with all of the billionaires throwing God knows how much money into launching people into space, mostly them, what are the hazards and or likelihood of success in living in space? Is kind of where this this talk kind of looks at. And so we're just going to do it this way because it's not like a presentation mode. So basically what I'm going to look at is basic life support systems on Earth, because that's what NASA, the European Space European Space Agency, and many others are using as their starting point. So that's going to include matter cycle. All of us are engines, right? We metabolize, we eat, we consume. So then we'll take a look at the space environment and all the nastiness that comes with that. And then we'll take a look at some of the habitation systems going back from Apollo as a starting point, and then some of the quite radical new versions that they've got. So we live in air. Everybody's used to that. For those of you who aren't aware, climbing to the top of Mount Everest, roughly 10 kilometers up, is basically the top of the troposphere. It's a little bit further above that. And that's the weather location. That basically covers 90+% of the actual air molecules below that line. If you wish to get your astronaut wings, depends upon whether you're in Europe or whether you are in the US, it's a few miles different, but one is 60 miles up, one is 100 kilometers, which comes out to like 62 miles or something like that, okay? So you can get your astronaut wings in the US, but not qualify in Europe if you hit that like 61-mile mark, which I find very humorous. But the atmosphere, so we know it's got oxygen, we know it's got nitrogen, it's got carbon dioxide, water vapor, methane, lots and lots of things, argon. Some of it we use for respiration purposes and an active metabolism. Some of it plays the role of just maintaining pressure, which is what 75% of the atmosphere, the nitrogen mostly does in that regard. Okay. The lithosphere, again, is just all the rock that we live on. Okay. Now, it doesn't sound like something useful for a habitation module. However, the lithosphere does a large fraction of the slow, long duration matter cycle, okay, in the form of subduction zones, precipitating rock out of the water in the ocean, for example, right? Hydrospheric water cycle. So again, we have evaporation, we can have water precipitating out in clouds. So here's a quick question. Are clouds liquid water, gaseous water, or solid water?
Gaseous. Really?
Not a gas. If you can see it, it's not a gas.
Oh. Ice?
Either ice or liquid, depending upon the altitude. It's one or the other. So it's always a fun one that really messes with the grade school kids. But if you actually go through a fog and you pull your hand through it, what do you collect? Liquid water.
Yeah.
So that water cycle, which literally takes entire oceans and continents to maintain, has to somehow fit in a tin can to make it work, right? So they're trying to condense that down. And I am racing through a lot of things here. The biosphere, how organisms react with the atmosphere, with the ground, with the water, actually changes and affects the system. For example, rainforests in the Amazon. They're rainforests because they're already a forest there. The vegetation itself provides over half of the rain that the rainforest uses. The trees themselves, as they do their photosynthesis and then the consumption of the sugars, releases moisture out of the leaves, transpiration. And that moisture then gets recycled back into the atmosphere and provides half of the actual rain for that rainforest. So when individuals cut and clear out rainforest, that vegetation is no longer there to provide the rain that made the rainforest possible. And so we're learning slower than we need to about the effect that the biology has on the what we thought was a water heavy location. Okay, so there are things like that that play a role. Matter cycling, and this is just a small fraction. You've got things like iron that are going to be absorbed into surfaces. Mars, for example, has a lot of rust. It's reddish color. You have carbon dioxide that can be absorbed via organisms and then laid down in the base layers of the ocean, like the abyssal plain. And so the primary removal of CO2 on the planet is a really slow, wait for phytoplankton to die, settle to the bottom of the ocean, and take the carbon with it. So it can be removed from the atmosphere naturally. Growing plants help us, but most of it that gets sequestered happens via the ocean process currently. Otherwise, you have to have things like a peat bog that build up over time to sequester it. And eventually you end up with coal deposits or oil deposits, depending upon the particular vegetation that's buried and the length of time. These are only a small fraction of the atoms or ions that get cycled on the planet. In the space station or what have you, right? So we'll take the humorous one, cows, right? They make some interesting smells, but part of that matter cycling, nitrogen, for example, we need it in the air, but we also need it to support the bacteria that supports the growth of the roots. And so that's another way to think about matter cycling. All of the organisms that we have are another way to consider the carbon piece. I already talked about that, so I got ahead of myself. And then the last one, phosphorus, is another primary piece of the matter cycle. We generate lots of phosphorus for the purposes of fertilizers, for example. It's probably their biggest use, but there are other industrial uses. That phosphorus then gets released, becomes runoff. You can get algae plumes, which become a problem, but those algae plumes then create dead animals and phytoplankton that sinks to the bottom and then recycle. Again, a lot of these cycling processes on the Earth literally take thousands of years to move it from the atmosphere to the water to the land. And then if it gets buried in the land, you're waiting for a subduction zone to move 1 million or 2 million or 3 million years later and drag that tectonic plate under, and then the volcano kicks it out again as gas, right? So the matter cycling on the planet is, on the quick scale, thousands of years. On the long duration scale, millions of years to rotate through material. Astronauts do not have 1 million years to wait for that rotation. So we have to find ways to make that happen quickly, okay? So that's what we know on the planet. That is essentially all of biology and chemistry in 5 minutes, right? What do we know about the space environment, which I think is more interesting for us here? So there are 4 major demons oftentimes referred to for people who are trying to live out in space, okay? Radiation. Star Trek's new one with Leonard Nimoy replaced with, what did they add, the new actor's name, talks about space being just death and demise, hidden in darkness or something like that. And he's right. So the sun, which gives us life, provides proton flares, coronal mass ejections, just a constant stream of really nasty ionized charged particles coming towards us at close to the speed of light, let alone gamma, X-ray, UV, IR, the whole electromagnetic spectrum, right? Beyond the sun, we have the joyful effects of the galaxy as a whole. Believe it or not, our sun's magnetic field actually protects us from a very large fraction of the galactic bombardment that's coming towards us. All of those black holes with jets and things of that sort are screaming out additional particles towards us. So the Earth's magnetic field plays a little protective shell around the Earth, The sun has its own magnetic field that plays a protective role around our solar system. With that being said, cosmic radiation is still quite dangerous. All of my notes are not with me right now. So otherwise, I would give you the statistics on the likelihood of cancer from that radiation. But I think it's like a few percent extra. Yeah, so the background population on Earth, if you live at ground levels, about 20% chance of cancer. If you're an astronaut, they're willing to let you have a 1 to 2% increase in cancer. They had to get an exemption from the EPA.
Wow.
Because the actual limits for people who work at like nuclear reactors or work as the rad tech have a much, much lower qualification. And one flight to there and back again puts you right outside that limit. So astronauts have already willingly accepted an additional 1 to 2% increase, which, you know, the background's already 20. Okay.
Yeah.
They like taking risk anyway, so it's what they do for a living. So that's the radiation environment, right? Gravity plays a role, and I have mixed feelings about how a lot of the literature describes this. So microgravity is this perception of free fall that you have when you are in space. So you and the spacecraft are basically falling at the same time, like the elevator ride, and so you don't actually have a floor underneath of you. And right now, all of us are experiencing not necessarily gravity, but rather the normal force pushing up against us from the chair or the floor or whatever's keeping us from falling through. And it's the normal force that's pushing up against us that keeps us from falling forever. That is what we perceive as weight. If you didn't have a floor underneath you, like the elevator ride, you don't feel like you have any weight. Okay. Now, if you're truly in the ISS or the old shuttle or Apollo or any of the other spacecraft we've got, so long as the engines are off, you're in free fall. Okay. And the lack of normal force that your body has to contend with really messes with every one of the body systems. Okay. Now, currently, all of our data is basically understood on the space station. The time to the moon and back, 3 days there, 3 days back, was also basically free fall. Once the engine's fired, you were on a falling trajectory either towards it or a falling trajectory back home. They only were on the actual surface of the moon for a day or a few days at most. And so the long-term effects of low gravity, not microgravity, but low gravity conditions, we don't actually know. All of our understanding is based on free fall or true microgravity conditions. And there are a huge swath of biological effects that come from that. So one of those is your cardiovascular system, okay? Anybody who works on their feet all day is really familiar with this one. You can feel the swelling and the pressure in your legs if you've been working and standing all day at something. My years working in a machine shop in grad school, and you're just standing in front of the mill for 3 or 4 hours straight, you can feel it at the end of that period. Well, your body basically has extra tension in the legs to help force that blood back into your brain. When you get into a microgravity situation, that process overcompensates. And you now have excess fluid, blood, lymphatic, all of it, processing much heavier in the top. So photographs of an astronaut when they first get into space, you can see their faces kind of look like they're chubby, bloated, kind of good, right? Mm-hmm. So not only do they actually have a lot more pressure, relatively speaking, or more fluid, I should say, pressure at the head with their cardio, but your eyes are also pressure systems. They're also affected by that shift in fluids. And so many astronauts have temporary loss of quality of vision when they go up. Most recover 95% of what they had when they come back down, but there are cases of astronauts where they go up and have degraded vision because of the pressure shifts, and when they come back down to Earth, being in the presence of a gravity well doesn't put it back to normal. So there are some long-term effects of individuals like that. So that's just one example of the gravity challenge. Space debris, right? Thanks to literally every man-made satellite we put up there, you are in a shooting gallery, okay? The blue in this haze are all of the trackable objects. So these are about 4 centimeters or larger that provide some kind of radar signature. And they are actively tracked by NASA and every space agency, okay? 4 centimeters does not sound like a very large object, but in orbit, you're literally traveling the equivalent of Mach 15 or thereabouts, depending upon which orbit you're in. A baseball traveling at Mach 15 will blow up a tank, okay? One of the more interesting pieces of that is this is a piece of aluminum, okay? And if you fire a paint fleck, you know, like you've been sanding at home and there's a little bit of paint, but you fire it at those kinds of ballistic speeds, that's what it does to a 6-inch thick sheet of aluminum. There are some photographic evidence of what they figured were paint flecks smacking into the orbiter windows, leaving huge craters. So it doesn't take much. I don't know how familiar you are with kinetic energy, but it's mass and velocity squared. And when you start having hundreds of thousands of miles an hour, v squared becomes a really nasty value, okay? And so the interesting thing about that is space is mostly empty. But the random chance of getting hit by something now is increasing drastically year by year. A lot of it has to do with really poor choices by governments, ours included. But China's done it, Russia's done it, I think a few others, where they've intentionally targeted a satellite and shot it and blown it apart. And now you've got 5,000 extra little bits flying around, all traveling at that original orbital velocity, plus or minus a couple hundred miles per hour, but 15,000 miles per hour, plus or minus a few hundred, it's still 15,000 miles per hour. And so that type of behavior, at some point, if it's not checked, becomes a chain reaction. It's kind of like a nuclear reactor, how tight you pack the particles in there. So long as the uranium is far enough from the next uranium, from the next one, from the next one, no chain reaction, life is good. But if you get them too dense, then there's the jump to the next one. And so then there's this question of, at what point does the explosion of one satellite trigger the explosion of another satellite, which then triggers the explosion of another satellite? And then you just have kind of like the movie WALL-E, where space is just filled with all this trash. There is that question of when we hit that threshold. Currently, we're not there, and there are currently space agencies looking at ways to trash collect. Vacuum of space, okay? Vacuum will kill you. Yep, that's really, really accurate. Movies do an interesting job of presenting it in TV shows, but vacuum will kill you, okay? So the vacuum of space has a lot of things going wrong with it. A, there's no oxygen, so you asphyxiate. That's a no-brainer. 2, you, as an individual, are a high-pressure vessel. You're on Earth. The evidence, if I prick you, which way do you leak? Out, right? So we, as an existence, are typically a higher pressure system. With that being said, our lungs are designed for 1 atmosphere, thereabouts, of pressure. If you're in a vacuum, if you tried to hold your breath, you would have a really bad day. Because 1 atmospheric of pressure, 15 pounds per square inch, 1, 2, 3, 4, right? You can start adding up a lot of square inches really fast on your chest. Go boom, very bad day. So if, perchance in your future, you are kicked out of a spaceship without your suit, don't hold your breath. That will gain you a few seconds of additional life. Not a lot more, because unfortunately the vacuum of space is an all or nothing thing when it comes to heating. Either you're roughly at 3 Kelvin if you're in the shadow, which is colder than liquid helium, or if you're in the sun, you're pushing 400 to 500 Kelvin. So you're either an icicle or burninated, right? There's not a lot of in between. And so the vacuum of space is very, very dangerous. NASA has an estimate, again, on the order of how long you can survive in space. And they just really don't want to publish it very often. So you can dig and find it, but it's something on the order of about 10 to 15 seconds. And in that time, you will still likely be recoverable and able to be resuscitated, but you will have permanent eye damage. You will have capillary bursting on all of your body. If you let out the air, there's the question of whether or not your lungs froze and the surfactants damaged, right? So they really, really, really want to avoid pressure loss at all extents. This graph I picked out of text, which is probably the worst graphic possible, because there's no way to actually interpret what they mean by this. I will try to interpret it for you as best as I could after reading many, many hours and figuring it out. What they're trying to demonstrate with this graphic is that different body systems, so the neurovestibular, so like your ear sense of balance, fluids and electrolytes, which are more than just your blood, okay? Cardiovascular system, so blood pressure, things like that, lung response, red cell mass, quantity of red cells, bone mass and muscle mass, things like that. What they're trying to show is that the body is an adaptable machine. And so there will be this initial spike where all kinds of crazy physiological effects happen in the short term, because your body's trying to adjust to microgravity or other conditions. And then as a function of time, the body will reach a new set point, which is what this 0G set point is supposed to represent. Sometimes it actually gets to a value that approaches the original value, like your red blood cells really diminish, and then over months, your body figures out what's going on and is able to produce them again at the right value. That one actually recovers over a long time. Other things, such as bone and calcium metabolism, continues to diminish day after day after day after day, even with massive amounts of exercise and dietary effects and other medical interventions. Even with every intervention that they come up with, you're still losing bone mass. That calcium then gets put into your bloodstream. That's a lot of extra calcium in the bloodstream. Now your body has to deal with that. So that has effects on kidney function and other areas. And so it's an interesting chart. Basically what it comes down to is microgravity is not a successful place for humans, is what this comes down to. Subjecting astronauts to the ISS for years and years and years now, we can unequivocally say microgravity is a really bad deal. Most astronauts, when they return back to Earth, especially if they've been up for several months, 3 to 6 months is a typical long stay on the station, up to a year at the most for some folks who are trying to do some unusual medical testing. In every one of those cases, they do not have the same metabolism same body mass, same bone structure, or any eyesight characteristics that they had before they left. They have permanent damage, even after years of rehab back on Earth. So that sounds really horrific for people who wish to go to space. With that being said, these are just what we know happens in the microgravity conditions. Okay. So basically, good. How long do you want me to go? Where do you want me to stop at time-wise, so I don't go too far?
Maybe 10, 15, 15 minutes.
Yeah, it's almost 8:30.
So 8:45-ish, 8:40, where do you want? Okay. Because I know I'm starting with a much shorter time than normal. So we know we need food, we need water management, waste management, fire detection, crew safety. I kind of like the next couple of graphics. It's basically what's the bare minimum you need for somebody for 12 hours to not die? What's the bare minimum for 7 days? What's the bare minimum for up to 3 months? And okay, we're really talking long term. How much do we need to cover? And going long term, you basically have to mimic the Earth's system in a small tin can with a finite power supply and no or very little resupply, because it's really, 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 really expensive. So when they think about missions, they look at the number of crew, the number of days, how leaky the spacecraft are. So my PhD work, I did a lot of vacuum cryostat work and worked with liquid helium and liquid nitrogen, and we could be happy with the leak tightness of our systems. And we're talking atoms, per hour kind of stuff. We were really, 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 really excited. That spacecraft, no matter how well they build that thing, is still leaking like a sieve compared to that really nicely crafted cryostat I have in the lab. Every time they do a spacewalk, no matter how much they try to pump out of that airlock, they're still losing a huge quantity, right? We don't think of metal as a porous material, but those atoms are wiggling and jiggling, even in a solid state, and an oxygen out here can drift through the metal to the other side. Doesn't happen quick. That's why we're using metal as opposed to something else. But you do just get a leakage literally through the skin of the spacecraft. So even if all the seals were perfect, you would still leak material into space. So that's something that has to be covered. So that resupply starts to become expensive. Basically, you come down to how long do you want to be out there? And so there's this trade-off. Are you doing a backpacking trip where you are taking every food item, every ounce of water, all the fuel for your fire, right? You're carrying everything with you. That works great for a 1, 2, maybe a 3-day overnight. If you're starting to go for like a week where you try to do the Appalachian Trail, you do not carry every gallon of water. You stop at the stream and refill. You start to pick the blueberries and the blackberries, and you know that there's this thing on the side, whatever it's called, that you can eat, but you saw this from somebody on YouTube or whatever. And so you pick up supplies. And so there's this time interval where when does it make sense to start recycling, right? 3 months tends to be the crossover point between a closed loop system and a open loop system. Now, open loop is everything that we breathe, eat, drink, consume, gets brought up by a supply vessel, used once, discarded. Highly inefficient, but really easy to engineer. Okay, worked great for Apollo and earlier sessions. Then you have something called the closed loop, which is like the holy grail, you could call it, where everything gets reused. Your pee becomes the water you drink. The salts come out of that and get used. The nitrogen and other things, the carbon in your feces gets recycled into plant matter that you then eat as a salad, right? So complete total closed loop. We haven't gotten there yet. Nothing that we've made hits that closed loop criteria. We just have losses. We're not able to completely convert back into something else. Right now, the best we have is a partially closed loop. We're really good at recycling water. We're really, really good at recycling air. But they're not the heavy parts of the loop. The food tends to be one of the harder parts. So the daily life of an astronaut is probably regimented more than a sailor on an aircraft carrier or any other naval vessel. You get 20 minutes for this, half an hour for this. You will do this here, you will go there, you will do this. And they have this planned out weeks in advance. I know what my schedule is going to be like before I launch 3 months before. Because literally every minute is hundreds of thousands of taxpayer dollars. And so everything is scripted out. They do get sleep. They're nice about that. They're allowed recreation on the weekend. I'm not really sure what you can do. Watch a movie on your iPad, but you know, consumables. We are now at the point where anybody who's had an MRE or meals ready to eat from the military or the supply store, the meals the astronauts get are much better actually than an MRE. Basically, you've got hot cold foods, something like 300 plus different menu options. Not too bad. That's including, you know, breakfast, lunch, and dinner and snacks, but you know, that was way more options than I had in grad school. You know, hot dog today, hot dog tomorrow, hot dog the next day, free lunch at the school, and then back to hot dog, right? So, you know, far more complex system. Where we are getting to now is we are able to grow vegetation in space. Ish. The astronauts have been able to grow some lettuces that they were able to make a salad out of. They've grown a few other items, wheat, for example, but they're running into the challenges again of microgravity. If anybody here has worked in a greenhouse, you have, even if the greenhouse was supposedly a sterile environment, there is still some mold that gets in there, or some aphid that gets in there, or some obnoxious little parasite that gets in there. In the case of the space station, they don't really have to worry about bugs, but humans are a bioreactor. We already come with pretty much every mold, virus, bacteria you ever could want. And so the very environment that we're breathing out is also allowing for those pests. And so what they found is with the low gravity situation, normally moisture will fall down. Normally there are breezes that dry out the vegetation. And so mold and rot from that process is probably one of the biggest problems that they have to work on. And so that's one of the challenges that they're facing. Now this particular experiment used a soil ash type thing. And they were able to get some vegetation that they could eat. But it was not a lot. And by a salad, I mean, here's 3 leaves of lettuce. Congratulations. That was and they were very excited. That was the only fresh produce they had in months. Right? If you eat something, it's got to go someplace. So the current waste management system is that lovely looking device on the right. And I will not go into those lovely details, but they have to do it. What that means is, as an environmental control and life support system, let's see, we got a few minutes left. Let's see what's some interesting stuff. So for any of you who like engineering diagrams, a few engineers out here. So this is the ISS, all right, roughly speaking. Each of these colors corresponds to one or more environmental systems. Those all get plugged together to be redundant. So there are CO2 scrubbers nearly everywhere. There are water, like dehumidifiers that are collecting it out of the atmosphere in several modules. There are temperature sensors and heating and cooling processes in multiple places. So those all are all kind of a redundant thing. But this is just the engineering simplified diagram for getting CO2 out. And this is the technology they probably have the best example of. So you've got to pass the air past a desiccant, so something that sucks out all the moisture, or any of the volatile organic compounds for that matter. Then that goes through another bed that just removes the CO2. Then you've got to compress it and filter it again. They have two separate systems that they have to change back and forth because one's being cleaned while the other one's being dealt with. These absorption beds are then heated, but vent out into space to get rid of the stuff that they don't want. And so it's a partial system. It allows them to remove the CO2 and the volatile organic compounds, but you're not actually keeping that carbon for the plants. You're not keeping that methane or other gases. And so that's just a simplified challenge. In terms of what we live on in atmospheric-wise, here on Earth, 78's nitrogen, 21's oxygen. So if you put those two numbers together, that's 99% of the atmosphere. All that other annoying stuff, climate change is caused by, and stuff that kills you, CO2, is less than that 1%. So they really need fine control over that troublesome 1%. Air pressure here on Earth, roughly 15 pounds per square inch. Okay. Mercury, Gemini, Apollo kept their atmosphere at 100% oxygen and 5 psi. That allowed for low pressure, which allowed for the seals on their space suits to be more manageable. Because under 15 pounds per square inch, that metal is just going to and stick out and not want to recompress for the joints. And so the spacesuits were at that lower pressure. Skylab, again, kept the 5 psi, but they moved it to a 70-30 to increase some of the nitrogen. Again, the Skylab was the living quarters. And so to try to prevent another Apollo 1 accident, they wanted to introduce more nitrogen to the atmosphere to keep it not quite so flammable. But in fairness, 70% O2 is a highly fire hazard. Okay. Space shuttles, they were pretty close to Earth standard, 20 and 80. They were kept at about 14.7 psi. So it was very comfortable for the astronauts inside the shuttle. But they had to do a breathing process to purge nitrogen out of their system and pre-breathe, kind of like a scuba diver has to do the air pre-breathing or post-breathing, I should say, because their suits were at about 4.5 psi, but 100% oxygen. That EVA suit is also the pressures that we see now today. Interestingly enough, I didn't have an atmosphere for the ISS, which maybe I just didn't look very well. There's probably right in front of me. The old Apollo suits, ginormous and bulky. They have an image that I think is really, really neat. There. So you've got many, many, many layers. One layer to keep you warm, one layer to keep you pressurized, one layer for abrasion. Repeat. Because if you get a break in any one of the other layers, you need to have a redundancy. Okay. And so they're basically wearing close to 200 pounds of armor, which sounds oppressive, on Earth. But in microgravity conditions, there's still a lot of momentum associated with that mass. Like if you get your arm moving, it takes a lot of effort to stop it, but it's not overbearing. On the moon, they were able to hop and skip 10, 15 feet at a shot, like a bunny. Right? So I've always thought that was an interesting thing. Let's get to, so this is just a small smattering of the various physical exercises that they have to go through. They've got basically your custom gym, right? That is meant to train, work, and maintain every muscle group you can think of. And even with 2 hours, hour every day or more, depending upon the particular mission they were on, they were still doing muscle loss, right? Every day in the gym for an hour, and they were still losing muscle. The bone was more drastic, and again, that's much harder to work with. Future plans. So believe it or not, there are study groups out there looking at bioregenerative, which is kind of where you take that vegetable pod thing and you build it into the CO2 scrubber and you build it into other aspects where you're able to filter the atmosphere. There are many plants that actually naturally take volatile organic compounds out of the atmosphere, turn it into plant tissue, and then recycle the carbon and the oxygen that way. There are studies on hibernation. We've actually done hibernation here on Earth accidentally. Ever hear of these TV stories of some poor kid or person who falls in the icy lake? The lucky ones are the ones that have their body temperatures drop fast enough before they ran out of oxygen. They went into a coma hibernation state. And then if the rescuing team has the right equipment, you can introduce the oxygen at the speed appropriate for the body metabolism increasing. If you slow the metabolism down, you don't need as much oxygen, right? So we've done it accidentally. We're not so good at doing it intentionally. I think there's a lot of forms that have to be signed. Somebody willing to put yourself through that danger. Artificial gravity. No, we're not Star Trek, but artificial gravity could basically go to 2001: A Space Odyssey, the rotating systems. Now, that's if you want a big space station. There are some plans for going to Mars because the travel time is 3 to 6 months, depending upon the trajectory choice, where they take the booster rocket and they don't jettison back to Earth. They use that dead mass. They peel out a big tether, maybe half a mile out, fire up 2 thrusters, and you get basically a bolo spinning in space. That would then grant artificial gravity or a normal force on the people living in the habitation module. That's a little bit of an engineering challenge because mid-flight trajectory changes don't work so well when you're doing one of these deals. So you would have to reassemble the system, take off the spin, and then do your trajectory changes, and then redeploy again. And so that adds a bit of a challenge. And then the last place that future plans is looking at collecting data on surface operations. We know that microgravity is hugely detrimental. How much gravity do you need to trick the body into behaving physiologically correctly? Do you need half? Do you need a sixth? Like, what's the lower limit? Because you don't have to have 14 pounds per square inch to breathe. Everybody who lives in Colorado and Denver, they're not breathing that. They're getting at 85%. They live perfectly fine. There are lots of other people who live higher than that, and so lower pressure. So there are lower values that we can get to, but we just don't know what that threshold for how much normal force or how much gravity we need for the people. So that's kind of very quick slapstick version of that talk. If you are curious, I can share a couple of nice books. Eric Seedhouse puts out a good book on life support systems. There's another book called The Moon, Resources, Future Development Settlement by Shrunkenall. Use of extraterrestrial resources for human space missions. So that's looking at how you dig up moon rocks and turn it into oxygen or aluminum or whatever you want to get out of it. And then the Lunar Resource Source book was printed back in '91. So that's like ancient compared to those others. It is still probably the Bible when it comes to understanding moon resources. Nobody's come up with a better version of that, interestingly enough. But that has a lot of really cool stuff in that in terms of mineral contents and things of that sort. So there you go. That's what I got.
Thank you.
Nice film.
All right, so I hope I didn't lose too many people online. I don't know if you guys want to do questions or not, but we got other things to get to, so whatever.
Any questions for Paul before we let him escape? I kind of put him on the spot. He did a terrific job.
I appreciate it. Thank you.
I'll never remember your last name. I'm sorry. Yeah. And it was great for him to do this for you. So I'm told we have something to stick with.
I'm a member. I should get all these things.
Huh?
I'm a member. I should get one of these things.
It's too bad you're getting this.
You're getting I didn't see you on the membership list. Did you not renew your dues, Paul?
So maybe
Well,
not.
then he's eligible, sure.
What gas for your car instead?
How do you bring one here?
Oh, yeah, he's ready for extra.
As a scientist, you have to have one of these.
Yeah, I always carry that. I always carry one.
Swiss Army knife, yes. We're a multi-tool person. Oh, wow, look at that. Very cool.
Jim makes them on our 3D printer.
Very, very cool.
Very nice.
Yeah,
Very, very nice.
yeah.
Thanks again.
Very
You
cool.
bailed us out. I don't have to sit here and do a little vaudeville action. You're pretty ugly.
Hey, I have a question for you.
Sure.
So, you've probably heard about the whole dust stuff about Elon Musk and, you can go to Mars and you're not going to be able to have a colony. Yes, I am. No, you're not. What do you think about,
Okay.
given
So-
our technology or future technology, whatever? Are we going to be able
So-
to have a colony or it's sustaining or is that
Mars is as difficult, if not much more so than, say, Antarctica.
yes.
Right.
Yeah.
So Neil deGrasse Tyson is right. You're not going to have easy family living on Mars. Terraforming Mars is going to be hundreds, if not thousands of years down the road.
Yeah.
The planet's just not big enough. It doesn't have a magnetic field. There's a lot of crazy engineering things that we're not going to fix anytime soon.
Yeah.
With that being said, people have figured out how to live in domes, i.e. submarines or Antarctica or other way stations. I see it not necessarily as a growing family colony thing, just because the cost. So the Billionaire Club might be pulling that off. But for the rest of us, it's going to be more like an oil rig or the Antarctic Research Station or any number of challenging, interesting, one-off type facilities. So you're going to have adventurers who are willing to pay for that experience if they can afford it. From a technology point of view, living on the space station is a nightmare. Trying to put yourself down on Mars or the moon, you actually have things that you can use. Space is empty. There isn't any resource except for the sunlight, which is its own problem. But the moon, you can get aluminum or oxygen or phosphorus or many other elements. It doesn't really have a lot of carbon, so it's very deficient in that way. It actually has water. So there are some resources that you could get there that we could use. Mars is way easier from a resource utilization point of view. It just happens to be really, really far away. And so there's that concern of redundancy, because once you're out there, you got like a year and a half for safety rescue, because they have to build something, launch it, and then wait for the trajectories. At the best of times, it's a 3-month trip given current technology. If we go to nuclear thrusters, we may get it down to a month and a half. If you want the most fuel efficient, so you're doing cargo, you're talking the 6-month trip.
Yeah.
So doable for smaller populations, for the adventurers, maybe a vacation hotel, not so much family living,
Yeah.
not for a while.
Yeah.
Because the technology required to figure out how to live on Mars in that way would be really, really useful to put to use here first.
Good.
If we can figure out how to terraform Mars, we can probably fix Earth.
Yeah, we'll fix Mars first.
So that's my 2 cents. They're both
Okay.
right.
Yeah.
We
Okay.
could live there. It's just a small number of we.
Yeah.
Maybe there's hope for us yet.
There is. I would sign up in a heartbeat. I have no doubt about that. After all the deadly things I told you, I would still sign up.
Yeah, when I was younger. I signed up for the army and that was an experience. 2 years, and they said, here's your M16, that's a Huey, get in it.
Wow.
So, good question though.
Any other questions for Paul? Did you enjoy the meeting after all? We had a great meeting.
Yeah.
And it's nice though that we're meeting back again and we're at Purdue now and maybe someday we can sneak over to St. Francis.
Either way.
Yeah.
Got more majors here though.
So thank everybody for attending the meeting and the people online too, if you're still there. I appreciate it. And I think we had a successful first in-person meeting here. And hopefully we can get our speakers lined up with the proper dates next time. So I guess that's it.
Thank you. Nice job.
Thank you.